Welcome back, our final day together. This is wonderful. We will get started with our morning session on deforestation, and I hope you'll see these wonderful connections between land cover and the importance that plays in all the things we've been talking about. We have a couple of slight changes to our schedule, no big deal. We'll have 3 talks this morning, and then Venkat from National Science Foundation will have a few words. And as you know, we are deeply grateful to NSF. And if you notice, I'm wearing my NASA shirt this morning. Sorry, I don't have an NSF shirt. I need to get one. Venkat, help me. And we're deeply grateful to NASA and others for helping us. And then we'll have the posters and a discussion. And just before lunch, we'll have a special presentation of some ancient historic data, which I think will be very important to us. So let's get started.
Hey, thanks again, everybody, for being here. And so this morning is Deforestation and Hydrology. And without further ado, I'm going to start with the first talk. Noel, Aloysius is going to talk about impacts of deforestation on the runoff. Thank you.
Right. Good morning, everyone. Thank you all for being here. Thank you, the organizers, Doug and all, for giving me this opportunity. I'll try to explain some of the things that I have been doing for the past several years. Before going into the presentation, I would like to acknowledge my collaborators and partners and friends at various institutions, particularly Jim Sayers, my PhD advisor, and Nadine Laporte, who is here, who has been a mentor over the past several years, almost 10 years now. Moving on, so today's discussion is about deforestation and its impact on the hydrological cycle, particularly runoff. And I'm going to show some of the simulations that we have performed related to this hypothesis. The first part of my presentation is I will present to you about a hydrological model development, its data inputs, and how good the rainfall runoff relationships are, and then move on to present some of the results. Just to give you an overview of the study area, we have seen these maps very often during the past 2 days. Just to give you an overview, the watershed is about 3.7 million square kilometers. About a third of the watershed lies on the northern hemisphere and the rest in the southern hemisphere, which gives a unique hydroclimatological relationship that is unique to this particular larger river basin. Looking at the rainfall distribution, which is the primary driver of the water cycle, there is an asymmetric distribution across the latitudes, and if you look at the spatial distribution, there is substantial variability in terms of seasonality as well as magnitudes, which is a key factor in determining how determining the rainfall runoff partitionings. The first part of my presentation is about developing the model, testing and validation, and then a series of deforestation simulations that I performed using this model. Just to give you an overview of the data sources, the work is already published about the model development and validation. I can talk to you afterwards, or please refer to this publication. However, the key input data are shown here: the topography, land use, and soil resources, which are mostly sourced from already available resources. The climate data is part of the reanalysis data at daily time steps. The simulation period that I'm going to present today is for a 59-year daily time series from 1950 to 2008. In addition to the climate and other topographic data, we also collected river flows at various locations within the river basin, information on lakes and wetlands, and all those things are used to develop a hydrological model that more accurately simulate the reality. The simplest form of a framework that we adopted here is shown here. Most of the reservoirs and fluxes are shown in this figure, and all these different fluxes and storages are included and modeled using all the available data. Going back to the watershed again, I would like to highlight, as I mentioned earlier, about a third is in the northern hemisphere and the rest in the southern hemisphere. If you can see, most of the highlands are in the southeastern part of it, which also have a series of well-connected lakes and wetlands, which makes the hydrology unique on this part, whereas if you go to the central Congo with a series of wetlands, that makes it another unique part of the river basin, which we discussed in details during the past 2 days. I'll describe you briefly about the model development. We delineated about 1,600 watersheds based on the topography, 90-meter digital elevation model. Each watershed is further divided into hydrological response unit based on 3 characteristics: the topography, land use, and soil type. So you can see the smallest unit here is the hydrologic response unit, which is about close to about 9,000 smaller units, which is the smallest spatial unit based on which the water accounting is done. The area of these hydrologic response units varies from about 10 square kilometers to about 20,000 square kilometers, the largest being for the largest water body, that is Lake Tanganyika. We also included 16 larger lakes for which there is information, some form of information available. It's storage-discharge relationships. We also included about 300 watersheds with wetlands based on the land use map, as you can see in this. Most of the wetlands, the tropical wetlands are here, and then there are a series of wetlands both in this part as well as in the southeastern Congo. Further looking at how the water is routed, if you look at this headwater region here and looking at a blow-up of that, each of the smaller watersheds has one stream segment which captures all the runoff and then route it to the outlet of the watershed through this stream segment, which again provides an input to the downstream segment, and so on. So the routing is in a sequential form based from headwater streams towards downstream. So there are, in this modeling framework, there are about 1,600 stream segments that moves the water along the river basin. As I mentioned, the model is run at daily time step from 1950 to 2008. It's a 59-year time series, during which we have information of monthly stream flows at 51 gauge stations. The smallest record varies for about 5 years to about 55-year time series, which is used to calibrate and test the model performance. We used only about 20 gauges to calibrate and used a 7-year data set, 7-year monthly time series to calibrate, and then the model was validated outside the calibration period at 51 locations, which are shown in this figure. I'm going to take some time first to describe what this is. This is the calibration results. The figure on the x-axis, what I show is the annual catchment average runoff in millimeters per year. And on the y-axis is the simulated runoff. Each point shows the average value with the vertical bars showing the simulated variability. That is one standard deviation. The horizontal bar shows the observed variability. It's again one standard deviation. The color code here shows the monthly values of Nash-Sutcliffe efficiency, which the good values varies from 0 to 1, 1 being a perfect fit of the observed monthly values. More than 30 gauge stations shows a Nash-Sutcliffe efficiency value of 0.5, which is considered acceptable simulations. For example, if you look at this particular gauge here, the dark red, which has an NSC of about 0.8, which also captures both the monthly interannual monthly variability reasonably well. Overall, if all these points lie on this one-to-one line, that means we have an excellent model performance, whereas if they go farther away, like here, the model performance is slightly poor. Overall, what we see here is a good agreement with simulated runoff across various parts of the basin. I'm just going to show you the runoff simulations at these 8 locations that captures the spatial dynamics really well. What you see here is the gauges at Oeso and Bangui. The monthly climatologies are shown here. The peak rain runoff season is September, October, November. This actually accurately matches the observations. So you see the larger peak, the flood runoff occurs mostly towards the end of the calendar year. Moving on to the south, here in the Kisangani, in Kisangani, it's the exactly opposite, where the peak runoff happens during March, April, May. Similarly, some other gauges further south in the southeastern part, and as a result, because of the asymmetric nature of peak runoff, we know that the Congo River Basin has a double peak. One, the higher flood season is March, April, May, the main river, September, October, November, and the secondary peak is in March, April, May. Overall, we think the model captures the spatial and temporal variability of runoff rainfall relationship well. Moving on to the next section of my presentation, using this model, using the same historical period, 1950 to 2008, we conducted a series of deforestation simulations. There are 3 of them that I'm going to present today. One, as you can see in this map, the darker green areas are classified as rainforests. There are about 12 different land cover types that are included with their physiological features, their different vegetation characteristics. These particular simulations are performed only on the rainforest catchments, which occupy about 45% of the river basin. For the first experiment, or rather simulation, what we did, we changed we changed the parameters such a way that the goal of our hypothesis, which is about 30% deforestation, the parameters are adjusted such that the change in land use varies from about 1% to about 30%, such a way the ET and surface runoff characteristics are altered. For each of these experiments, we conducted 100 simulations. The first is all over this rainforest watershed, excluding the central basin, that is the catchment area between Kisangani and Kinshasa. We did not alter any of the parameters there, assuming that we are going to keep the central part of the core of the rainforest intact. Most of the peripheral areas, we modified the input parameters such that it mimics the deforestation that's going on here. So the first one is all over across the whole river basin. Second one, we focus only on the northern part that drains the Oeso and Bangui catchments. Second is the southwestern part that drains the gauge at Bandundu and Port-Franc. Again, the simulation period is 1950 to 2008. I'm going to present you some of the results. First is the northern part of the river basin. What you see here is, in the simplest form, what is the rate of change from the baseline. Baseline is considered the non-deforested baseline simulation that I presented earlier. What I'm showing you here is at the gauge station here in Kinshasa, what is the rate of change, average rate of change of monthly runoff in cubic meters per second. Overall, when you change the land use from 0 to about 30%, there is a distribution which varies from about 0.1 to 0.6%. So there is a smaller change when you only when most of the deforestation is concentrated only in the northern part of it. Just to look at what's going on at the Bangui catchment, we see a larger change which does not translate into substantial reduction in Kinshasa. What you see here is this is at Kinshasa, the top figure. The second bottom figure is at Bangui catchment. The average runoff there is about 5,000 to 6,000 cubic meters per second. So that does not substantially alters the runoff downstream. Looking at the southwest, which is the Bandundu and Port-Franc catchment areas, what we see here is again some similar distribution but slightly different, similar range but slightly different distribution within the 100 simulations. Here also we see not so dramatic as in the northern part, because as you can see there is less areas characterized as rainforest, which could be a reason. Overall, when you look at, when you modify the landscape or deforest across the whole north and south, what we see is an overall about 2 to 3% reduction in flow in Kinshasa. So that when there is substantial reduction, we are looking at about 41,000 about 40,000 cubic meters per second average discharge. You would see a reduction which varies from about 1% to about 5 to 6% flow reductions. So these are some of the results which, in concluding, what we need to see is rainfall. Some of the uncertainties that I want to mention here in these simulations are this: we assume the behavior is the same in the baseline as well as in the deforestation experiments, whereas there could be changes in the microclimates as a result of extensive deforestation, which the land surface atmosphere coupling is not modeled explicitly in this work. That adds to the uncertainty. There is also increasing, will the deforestation increase infiltration rather than producing excess runoff? However, there was a study about a year ago in the Amazon based on observations. What they're looking at, the goal of that study was to look at if there is an increasing rainfall, how does that translate into whether it's increased ET or runoff. Their conclusion was if there is an increase in rainfall, it will translate into more runoff rather than enhanced ET. when it's the same analogy, I would assume there is more, the response is more towards runoff rather than the evapotranspiration flux. So there could be some belief in the increasing runoff hypothesis here. I'm going to change slightly about the focus of the work, trying to see how this deforestation play into. There is logging as well as the other aspect is agriculture, which under current conditions, it's very low in productivity. So one of the goal is, if the deforestation is largely going towards, one of the key factors of deforestation is to produce more food. How does that affect the water dynamics in the basin? This is a slightly different focus, but I'll try to connect the dots back towards the end of the presentation. So the key assumption here is pretty much 95% of the agriculture is rain-fed, and there is not substantial irrigation going on there. And our goal is improving agricultural productivity to limit land conversion, particularly in the rainforest areas. As I mentioned earlier, the present status of agriculture is due to the poor quality of inputs, stagnant crop yields. The agricultural activities are predominantly rain-fed. As a result, the potential crop yields are not achieved. It's nearly at 25% of the potential. Agricultural expansion without productivity increase leads to land conversion. Therefore, we are proposing that improving water management in the ag sector may limit deforestation. So that's the goal of the second part of my presentation here. Some simple equation I'm not going to go through, but what we did, we looked at 4 different crops, rice, maize, soybean, and cassava, which constitute about 60% of the daily calorie intake in this region. Our goal is, in order to double the current crop production in this, among these 4 crops, we need to supply at least 60% of the crop water requirements by these 4 crops. So if rainfall is not providing enough water to meet this 60%, how much water we need to provide by diverting other sources of water. For example, it could be a diversion from the nearby stream that provides the excessive runoff. Just to show you where these agricultural catchments are, these red shaded areas are the regions where most of the agricultural activities are going on. So what we do is how much water we need to appropriate in order to make these regions more productive. What we did, we reallocate available surface runoff from my nearby streams to meet the 60% demand. At the same time, considered the environmental flow requirements, excluded all the flood flows, and assumed that all the cropped areas are provided with supplemental irrigation that maintains the 60% crop water requirements. The monthly accessible flows that are diverted from the nearby streams varies from 5 to 40% of the accessible runoff, which exclude flood flows, as I mentioned, and off-season growing season, off-season runoff. I want to explain what these 2 figures are. Let's focus on the left side flow. What I'm showing here is the percentage of diversion across the whole agricultural areas from the nearby stream. If you divert from 5% to about 40%, how much water is available in depth within for all these cropped areas. We looked at 3 different irrigation efficiencies. And then on the right side, what I have is, for the same diversion, how much land you can cultivate with the available water. For example, if you look at, let's say 20% diversion at 60% irrigation efficiency, we have about 60 millimeters of runoff available at the field. Now, how does that translate into? We are able to supply irrigation to meet the doubling crop demands to about 1.8 million hectares. That is less than half of the current rainfed areas. So, key conclusions from this is seasonal water availability is a key constraint to maintain productive agriculture. Runoff reallocation is possible, but not feasible everywhere, particularly in the headwater catchment. And then our take-home message here is improving agricultural water management or improving agricultural productivity. It could be a key factor in limiting deforestation. Going back to my concluding slides, based on our experiments, the hypothesis is supported that increased deforestation may result in increased stream flows based on where the intensity is, the deforestation intensity is. Rates of increase are different in the northern and the southern part, assuming that the hydrological dynamics are different in the north and south. And then, lastly, agricultural water management may provide a win-win solution to contain deforestation. With that, I conclude my talk. Please contact me. And I'm also looking for potential PhD opportunities. If there is anyone, or you or your students are interested in pursuing a PhD on similar topics, please talk to me. Thank you.
Thank you. I think we've got time for one or two very quick questions. Are there any questions?
Could you explain sort of the empirical justification for things like corn crops being limited by seasonal water supply?
So could you repeat that again?
Well, you say the seasonal water supply is what limits the productivity of say, corn agriculture.
Mm-hmm.
So how are you grounding that in terms of like the agricultural system? Is it a monodominant crop? Is that the only thing they're going to cultivate? Is it part of like a Swidden system? Like what sort of agriculture are you imagining?
So in this particular simulation, what we did, if the distribution, so we assumed a certain amount of acreage for all those 4 different crops. We know the seasons when it's planted and harvested. Mm-hmm. During that time, we estimated the effective rainfall that is available for crop for during the growing season, and then estimated the deficit. That is not what is available, so to maintain the productivity level at 60%, right? To meet the 60% crop water requirement. So the total rainfall, and we calculated the deficit. Now that is only, we are looking at only the water aspect, but there are other constraints, for example, quality seeds, fertilizer. So it has to be a total package that addresses multiple factors, but here what I showed you is water is a key factor. Mostly towards the end of the growing season, when the rainy season ends, that's when the crops suffer mostly, and that's when the yields drop.
Interesting. Yeah, I would just strongly suggest you look into the other limiting factors, such as nutrients or things, which are much stronger in tropical.
Definitely,
tropical soils.
The soil fertility is a key factor. I mean that is another thing that we have to consider: how to maintain high fertile soil to keep the productivity high.
Excellent. Cool. Thanks for the presentation.
Thank you. I think we move on, and if there are any more questions, I think the poster session is a great opportunity for that. So our next speaker is Nadine. She will talk about industrial logging and linkages to deforestation. Thank you.
Could you put I'm not sure. Yeah, thank you. Good Good morning, everybody. First, I would like to thank Doug for inviting me. And the last few days have been wonderful. I learned a lot about hydrology and biochemistry that I didn't know much about. My expertise is in remote sensing. And I'm really looking forward to work with you guys in the future. I think we're ahead of a big challenge to understand what are the processes in the Congo, and it's very exciting work to do. So today I would like to speak with you about some work we've been doing looking at the relation between logging industry and deforestation. And also I would like to start to discuss about, I think there is a misconception between what is deforestation and degradation in the Congo. This is a Landsat image of the northeast of Congo. And as you know, we have a long time series of Landsat imagery, like 40 years, that I'm sure Matt Hansen in the next talk is going to speak about. But on this image, you can see that it's pretty easy to recognize degradation here along this straight line, which are logging road. You can see it's kind of this light green, which has a very different spectral signature than an area where you have like shifting agriculture here in red, and also here along this road. And as Doug was saying this morning, there is certainly very different energy balance between this degraded area by logging and this ag land. And in most, I think, hydrological model, tell me if I'm wrong, I think you have a simplification of what is on the land, and you don't really have a good representation on what is really the land surface. And I think with remote sensing, if we can work at higher resolution, we can help you to better parameterize these models. So the hypothesis of the 30% deforestation, I think the origin came from this paper, which is 10 years old. Actually, the 30% was 30% of the forest of the Central Africa region is occupied by logging concession. And the logging concession here are depicted in gray, and in red, you can see the logging activity. You can see that you can have a logging concession in the Congo, but you don't have necessarily activity in this logging concession. So I think we should think about that when we want to use general statistics and you put them in models also. I think yesterday during the discussion, someone mentioned RED, which is the reduction of emission from deforestation and degradation, which is a carbon finance mechanism. Country can get paid to reduce degradation and deforestation. And the big difference also when you speak about this policy is to differentiate degradation from deforestation. On this two diagram, you can see that degradation is a slow erosion of your carbon, if you want, but you still have a forest or some kind of very vegetative surface, while when you do deforestation or conversion for agriculture, you have a large loss of carbon. It's rapid, and it's in most of cases irreversible when population density are high. So in terms of processes and loss of carbon also, they are very different. So a little bit of history about the industrial logging in Central Africa. It started in the 70s, and it's kind of like a vague. It started from the coast, Gabon, Cameroon, and slowly moved inland. And this for good reason, because it's extremely expensive to move these gigantic logs across the landscape. Only very few trees are cut. It's extremely selective. It's very different from what's going on in Southeast Asia. It's 1 to 3 trees which are cut most of the time, mahogany type trees, where basically you can, the cost of moving this tree is possible because these trees are very valuable and the other one are not cut. So it's how it was 10 years ago. I think there is a trend now to cut more trees of so in the future you may see more cutting, but traditionally it was 1 to 3 trees per hectare, at the exception of Gabon, where you have Okume monospecific forest that allow you to have a more aggressive, I will say, logging. This is the situation in logging now. So again, this shows you where concessions are in the pinkish color. The blue are the certified logging concession, and the roads, the logging roads and the public roads are depicted in gray. What was interesting to me is to see that actually also most of the industrial logging in the region is outside actually of the Congo Basin, at the exception of the north-west part, which I think is the Sanga sub-basin at the border between Cameroon, Central African Republic, and Republic of Congo. So to test the relation between logging and deforestation, we use several data sets. We use what I call the old roads that were published in 2007, and these roads are from the 1970s, using Landsat imagery from the 1970s to 2003. And after we have what we call the new road, which all the logging that happened after 2003, also using Landsat imagery, but also other type of data that have been put together in the OpenStreetMap. And there's a young postdoc who is working with this issue with me, and he's based in Zurich at the university. So we cleaned a lot this data set to make it compatible with the old data we had. And in terms of deforestation, actually decided to use the 300 meters ESA, European Space Agency product of annual forest conversion. It didn't pick up MAT product, which is a wonderful product, because I think for part of the time series, we didn't have net deforestation. And I think Matt has been reviewing and revising some of his product now to have net deforestation. So basically what we did, we put a 1 kilometer, a very simple approach. We put a 1 kilometer buffer around all these roads, public roads, old logging road, and new logging roads. And we were interested to see the relation with deforestation or forest conversion depicted by the ESA map. On the upper right photo, you can see it's a traditional main logging road in northern Republic of Congo. It was taken in the CIB logging concession. And just underneath, it shows you how a skid trail looks like. The skid trail are small road. I mean, and they're not really roads. You have a like bulldozer, and they go to pick up the trees, and they kind of meander through the forest. And you have a lot of compaction of the ground, and they run above. I mean, on a lot of vegetation, but it's not really a permanent road. And it's illustrated on the lower left map, which was done using Iconos imagery, which I can show you here. So basically, this is a combination of 4 meters and 1 meter data. You can see very well in this composite color the swamp forest in blue, and the roads as straight line. In the upper left here, you can see the area that was mapped in the previous map. We see the little skid trail, sorry. So that's, again, I put quite a bit of photos because I don't know if most of you have been spending time there, but it's kind of nice to see how it looked like really the vegetation. So again, a logging road, abandoned logging road. Lots of these roads are abandoned when the wood has been exploited. A skid trail, and this one, the lower right one, I guess is of big interest for you. It's in one of the swamp forest at the southeast corner of the Tsanga Reserve in Northern Republic of Congo. So locally, this road at least have a very strong impact on the local hydrology. I'm not so sure that logging road at the regional scale have a lot of impact on the hydrology, but definitively at the local scale. Oops. So, like I was telling you, most of the roads are abandoned after logging. So this shows you also in northern Congo some of the images that are used to map this road. And also we use a lot of digital videographies to do some validation of maps we did like 10 years ago. And you can see on this image, on these two videographies, one of an active road and one of an abandoned road. And you can see you have a lot of vegetation on it. This is how they do. Generally they just put a big log across. It's important to close this road for two reasons. One is if you have high population density, people are going to move in there and put agriculture, and generally the concessionaire don't like that, because if you have agriculture, you don't have forest to cut anymore. And also it's important for wildlife. There is a lot of poaching. When you start to open this road in very remote places, people take the opportunity of this road to go deeper in the forest and do poaching. So that's a site of where a tree was felled, and you can see between 3 and 6 months later, you can barely see that. There is an opening, but you have a lot of regrowth, which in terms of evapotranspiration and water balance, I'm not sure if it's a lot different than the forest. I guess we should look into that. This is another, so there are examples of type of forest in the North Republic of Congo. So on the upper left, it's a very interesting forest. It's a monospecific forest called Gilbertodendron forest. It's very unique. There are very few monospecific forests in Central Africa. They are the tallest forests in Central Africa. They're extremely tall trees, lots of biomass. After, underneath, you have what we call marron-tassé forests, which are very different forests, are very open, and they have a very thick understory of marron-tassé, which also are used by lots of wildlife, like gorillas and elephant, and lots of animals like this type of and maintain this type of open forest. You have mixed close forest, what we call in our jargon, which is terra firme forest. And at the top, on the upper right, you have the raffia swamp forest, and these forests are generally always underwater, the raffia swamp. And I invite you to see, there is a very nice poster that was presented yesterday about the distribution of different type of seasonal forests in Central Africa. So it's very interesting work looking at the distribution of this forest and the relation with peat swamp. again, open forest with a logging road. And also what is interesting, I think, for hydrologists is what we call yanga. I don't know, anybody knows what a yanga is? So yanga is a terminology in Republic of Congo. For the topography, it's so flat that if you have a little bit of topography during the rainy season, the water, you don't really have rivers there, and the water just go to this lower topographic area and make this big, I don't know how you can call it in English, une mare in French, I guess. So it's very interesting, and these are important for wildlife, and also because they get water there, and they get also lots of minerals. So this is just a fast illustration of the progression of logging in the Republic of Congo between the 70s and 2003. So you can see the progression through the landscape in green. There are protected area, and what we measure is that in between the 70s and the 80s, the progression of this road was around 150 kilometers per year, and after around 2002, it jumped to 650 kilometers per year. So it can be very dynamic. In terms of the new analysis that Fritz Kleinström is doing now, you can see that in red, the new logging, in green, the old logging before 2003, and we found out that it doubled since 2003. And you can see again that it's mainly located, which makes sense, on the part of the Congo region, which is close to the coast, because of it's super expensive to do this kind of operation. And the good news, I guess, for the Congo Basin is that most of the Congo Basin still with very little logging, industrial logging. We know there is a lot of logging going on the eastern part, which is illegal, but we don't know much about it, and you cannot really map it using satellite imagery. So that's using the watershed that Noel used in his study, and you can see again that most of the hotspots of logging activities in the basin is very, it's very focused in one place, which is at the border between Cameroon, Central African Republic, and the Republic of Congo, mainly. So the hotspot, what was interesting also is that the hotspot of logging didn't coincide with deforestation, and it's mainly a public road. It's where we found the main relation. It was with public road. And these are showing the area where you find most of deforestation of agricultural conversion, while here you have where you have the hotspot here and here for logging. This traditionally shifting agriculture is along roads, public roads, but very rarely in this region. It's different situation in other continent, but in Central Africa, most of the logging road don't lead to deforestation. It's mainly along the main road. This is Iconos image of Epulu, which is in eastern DRC. You can see that the little blue dots are corresponding to a new deforested area around Epulu and along the road. So to finish, just some results to summarize. So the logging extent has doubled since 2003. 80% of the road developed prior 2003 were abandoned. The hotspot of road development do not coincide with deforestation, and we didn't find any causality. Logging road, old and recent, have relatively a low rate of deforestation compared to public road. and the highest rate of conversion were found in the DRC. And also I would like to underline a few points, like you should remember you don't want to consider deforestation as degradation in your models. I think the land surface properties are completely different. Selective logging in the Congo Basin is completely different from other continents. And you don't want to extrapolate or take for a long time. People have been using what's going in Southeast Asia, in Africa, and you don't want to do that, that's for sure. And the carbon fluxes, we did a lot of work on carbon, and I didn't present today, but carbon fluxes associated with deforestation and degradation are completely different in quantity and rate of flux. So again, you don't want to mix them up. And forest degradation from industrial logging is relatively simple to map, either by visual interpretation or digital classification. And to finish, I think it will be important for this working hypothesis that maybe we want to have sub-hypotheses to test for the watershed that Noel presented earlier, instead to have simulated data. I think we should try to parameterize. We have the data from MAT and some data from the mapping of industrial logging. I think we can parameterize better at the level of the watershed and start to look at actually what the impact, how much of the watershed needs to be deforested or logged to start to see an impact on the biochemistry of the river or the hydrology. I think we have the data set to do that. And I think yesterday we had a presentation of Rob Spencer that showed that in the Kivu region, he started to look at the impact of deforestation on the biochemistry of the river there. And I think what he found is very specific, certainly to the Kivu region. And I think this should be replicated in other places in the Congo where you don't have this topography or the geology, and you're going to find certainly very different biochemistry and also different hydrology, I think, and impact on the discharge. So thank you very much for your time. These are just small photos of this is in Congo, and it's a town of Mbandaka with rice crops on the upper left. On the right, it's when I was flying to Gemena in the DRC. So just enjoy the photos, and if you have any questions, thank you.
Thank you, that's great. Thank you very much for giving us these alternative hypotheses. I think that's great for the discussion. And so are there any questions?
Oh,
Maybe
yes.
one. Yes.
Yeah, it's really more of a comment, Nadine. Merci beaucoup, très magnifique. I really appreciate what you've shown here, and you are correct. The 30% number in the hypothesis was from your paper, and I really like the changes that you've suggested. So thank you. This is I really appreciate it. Thank you.
Thank you.
Any quick questions before we move on to the last talk? No? Well, there's oh yes, one.
Noel, bienvenue.
Nadine, bon, merci beaucoup pour ce que tu fais. Déjà, au niveau du RAID, en ce qui concerne notre zone, tes résultats sont beaucoup exploités et c'est très intéressant pour nous. Alors maintenant, je voulais juste faire un petit commentaire, notamment sur un avis qui peut peut-être contribuer pour la discussion après, au niveau de l'impact hydrologique, c'est-à-dire une pointe que le fait que on crée des pistes dans cette zone forestière et qu'après elles puissent refermer. Mais ces pistes, tu ne l'avez pas dit, quand on crée ces pistes, on crée des ponts naturels. Vous voyez, on abat des arbres et on fait passer de l'eau en dessous. Et cet aspect-là, généralement, déplace le cours des rivières. Et ça pose un problème parce qu'il y a beaucoup de rivières dans cette zone qui ont subi beaucoup de déformations et que quand vous déformez le cours d'un cours d'eau, ça peut entraîner des phénomènes après. Et ça peut avoir des incidences très significatives en matière d'impact hygrométrique et de la déforestation à ce niveau-là. Ça, c'est un élément important. Maintenant, l'autre aspect au niveau des arbres que l'on enlève dans les concessions, l'avantage c'est que tout est quand même cadré au niveau de notre zone. Vous voyez que, par exemple, au Congo-Brazzaville, nous avons une loi qui est très forte. Le ministère est très impliqué pour contrôler l'abattage des arbres. Et vous voyez que chaque fois qu'une piste est créée, automatiquement elle est refermée pour éviter ce que vous avez évoqué à ce niveau-là. Donc ça, c'est déjà un élément important. Si les pouvoirs publics pouvaient respecter ce genre de choses, insister pour qu'il n'y ait pas l'abus massif de ces arbres, d'abattre ces arbres, ça peut aussi permettre qu'il n'y ait pas trop d'impact sur l'hydrologie et la déforestation. Voilà un peu juste un commentaire que je voulais faire. Merci.
Merci beaucoup, bienvenue. Je suis d'accord avec toi, il peut y avoir un gros impact au niveau local, au niveau de l'hydrologie, et plus de législation, ça ne peut pas faire de mal. Donc oui, je suis tout à fait d'accord avec toi.
Thank you. Was there any quick question? No? Okay, so we move to the last speaker, Matt Hansen. It's giving a talk about space-based monitoring. Thank you.
Thank you, Doug and Guy, and everyone for having me here. My work is using the satellite archives, the free and open archives, to track land-covered land use change. And we have a project, part of a project based in Central Africa called CARPE, Central African Regional Program for the Environment. And it's been there. We're one of the University of Maryland, one of the founding members in the 90s, from Nadine. I was at the University of Maryland, and we've had this good fortune to work there for we're pushing 2 decades, and really filling up a data vacuum in terms of what's happening on the land surface using Earth observation data, satellite data. So it's fantastic work there. We work with University of Kinshasa in Kinshasa, University of Maringouabe in Brazzaville, a lot with the forestry departments, so SINEAF in Brazzaville, DIAF in Kinshasa, and they're coming to the University of Maryland this fall. So we're pretty present there. I was Peace Corps in what was then Zaire, which doesn't exist anymore, and what was then Bandundu, which doesn't exist anymore. But I speak Kikongo and Lingala. My French is comme ci, comme ça. But anyway, so it's a fantastic geography, fantastic people and Earth system. Our work is to track forest types, the rates of change, rates of loss, recovery, and the drivers. And the Central Africa is the second largest forest, humid tropical forest massif in the world. It's very different from the Amazon basin in terms of drivers, very different from Southeast Asia. But our idea is with the satellite to build up consistent records and start telling the story of what's happening and what rates of loss we're experiencing, mapping those and adding attribution to the changes. So I'll just give you some examples. This is a paper coming out in Science Advances in a few weeks where we are tracking what are the drivers, what are the land use outcomes of forest loss in Central Africa. And you can see by these colors, it's a neat little like gradation. As you get to the coast, you have this nascent but rapid increase in agro-industrial land uses such as palm oil in places like Gabon and Cameroon. As you go into the interior, as Nadine laid out in Gabon and Northern Republic of Congo, commercial logging is the driver. But if you're in DRC, it is 92% smallholder agriculture. So this is the deal. I call this Article 15 from space. Article 15 is the made-up constitutional right from the time of Mobutu, where he basically had 14 articles in the Constitution. The 15th one, everybody said, was "Débrouillez-vous," you're on your own. And this is 80, 90, 100 million people feeding themselves. So the pressure on the forest is immense, and it's really with axis, smallholder agriculture. And you see that in our maps and in these analyses. We also track what forests are being, what are the forest types that are being cleared, and so there's equal amount of primary forest being cleared compared to secondary reused forests in DRC. Most of the clearing, for example, Republic of Congo is primary forest that's related to logging. And the big deal is that these rates are going up. So over time, let's see if this thing works. Oops. Over time, we see the trend in natural forest, so the not secondary forest, the primary forest, the intact woodlands, going up and correlating with population, because that's what's happening. The folks are feeding themselves largely across the basin. And when the UN makes projections that DRC is to have almost 400 million people by the end of the century, if you take our areas of clearing and correlate them by population in the UN projections, the forest is gone by the end of the century. It's hard to do that, actually, to extrapolate numbers like that and expect the forest to be gone. So again, the demographic pressure is the big deal, the burgeoning populations and their self-reliance, going back to intensification, lack of intensification, lack of permanent agriculture and alternative management strategies. So when we compare DRC to places, the other two big countries, this is Indonesia, this is Brazil, it looks small, but it's more than half of what happens in Indonesia, and it's just under half of what's going on in Brazil. In terms of primary forest being cleared, and all of this is with axes, this is agro-industrial, so this is DRC again. So again, I can't stress enough how it's really impressive, actually, the amount of clearing by hand that's going on. So this is that story of the demographic expected trends and where we're going to be in terms of population. The idea that places like CAR and DRC are not getting they're not importing a lot of food. They don't have oil and gas to trade for food. So they really, again, a lot of the food index numbers really reflect a self-reliance that is unique and also leads to a dominant landscape of smallholder agriculture, shifting cultivation. I'm going to back up a little bit here and talk about where people aren't and give an example of the forests that are away from human pressure, and we call these intact forest landscapes, and to discuss what threats they have, and then I'll back out to more of the direct pressure of population. But all of these forests here are the primary forests removed from human presence and human disturbances, and the biggest changes in these landscapes are the logging that Nadine pointed out. So you have logging roads expanding over time, and they're certified. This is in the FSC certified landscapes of the EFO and CIB concessions. But the biggest thing to point out with these extractive industries is not necessarily that the footprint of the logging is small and maybe the forest recovers, it's gated and it's well managed. But in the end, what you've done is you've turned 3 small fishing villages into cities with their own populations that will be there. You've hardened the road and created great infrastructure to connect it all. You put in a dam to electrify it. So there is the bigger impact, I think, in terms of land use change and conversion of forest will be outside of the logging concessions. There really is a big infrastructure that's built around to support sustainable green logging. Just a slide to show that we work on carbon as well. These are carbon strata. No big deal. Now I'm going back to the agriculture domain and show some examples of the Swidden system from the point of view of space. This is the forest massif in DRC within which we have what we call, which is where we approximate sustainable shifting cultivation. Well, so when you look at the landscape, what we call the rural complex, where you have active fields, early fallows, maybe secondary regrowth, and then little bits and pieces of primary forest, and settlements and villages, this is the rural complex. And the rural complex is sustainable as long as you have an outlet to grow, or you have a kind of static demographic. So, but when we look at this landscape over time, you can see it expanding. And so as the population grows, new lands, this shifting cultivation landscape is extended out into the rainforest. Under a sustainable model, when we trade space for time, we get about 18 to 20 year fallow periods, which is the typical shifting cultivation interval where the forest can recover and you can revisit it after 20 years, cut it, burn it, and you can have another comparable crop to what you had the first round. But again, if that's not sufficient, you can go out into the primary forest. Outside of this domain, out here, there is no such outlet. So these are the really pressure points for people and the shifting cultivation system, and I'll come back to that in a second. So if people are the smallholders are making their livelihoods, we try to map also settlements and where people are explicitly on the landscape. So this is a 30-meter map of population settlement density, and then we turn this into population using demographic health survey data. But we're mapping all of the villages, all the way through the big cities, and we can do this using Landsat data, and then we can take a sample and make a population estimate using high-resolution data and allocating people per household, which we have from a demographic health survey taken by funded by USAID, and we can turn these pixels into a population estimate of 96 million. So again, trying to find exactly where people are inside the Congo. And so then we can combine everything together. We have the intact forest in dark green, primary forest close to disturbance, and these slightly dark green secondary forests in the brighter green. The settlements are all in blue, protected areas, et cetera. We can look at distance of remaining primary forest from settlements to find kind of ID the higher likelihood biodiversity rich places. We can track changes in the quality of forest inside and outside of parks. For example, messing up this name, but it has more disturbance inside it than outside of it as charcoal is being made. Virunga is also under threat of change, and Salonga is one of the more quieter landscapes. You can see that here. The forest is largely intact in Salonga. If we zoom in, we can take a look at places like the Eastern Rift, where populations and internally displaced peoples are moving out into the forest. And we see this along a whole axis from the Eastern Rift all the way over to Moringa Laporte up to the Ubangi River, where due to the war in the last 20 years, people have abandoned the trunk roads and moved out into the forest to get away from insecurity. And so this has big implications for biodiversity, for future development, obviously I think also for hydrology. I'm going to show the south here. This is a place, Bandundu, where the population density is very high. There is hardly any remaining primary forest or good forest to extend into. These fallows in the shifting system are so short, we don't see the disturbances most of the time. So we can get down to 8-year fallows in Bandundu. So this is a very heavily degraded, high population area. Kasai to the east is in a transition where you can imagine Kasai after a number of decades looking like Bandundu, but still patches of forest left. So differential pressures inside and outside of the main forest massif. I think we need to pay attention to that, because this band of population from Kinshasa all the way out to Mbuji-Mayi and down into Katanga is a heavily degraded, high population area. And when you're doing the farming and you see the rivers, bright red with clay. I love the graphic of the researchers. I'm sorry, I don't remember the name, but they took the old navigational charts of the Congo River, and you see all of this sedimentation, these increasing of the islands in the river, and is that lower flow or is that deposition? It's probably both, but certainly with more of this agriculture, more folks, you're going to get a lot more erosion. We also work on biodiversity. I don't need to talk about that. I just want to give the last bit to a hydrological application. Yolanda Manzimi has a poster in the session. She's my student working on a USGS model that is based out of Eros in South Dakota, where researchers are using Earth observation data to calibrate flow routing models. And it's called GeoSFM. And so if you have land cover, you have DEM, you have trim data, you can take it and try to calculate, wow, hold on. Calculate the entire basin's flow dynamic. So everybody showed these gauges. We have daily data at Kinshasa, daily data at Weso, daily data at Bangui. There's a couple steps in the process to try and get these hydrographs to line up very well. For example, when first building the model with the default parameters, it was too fast. We had to slow down the hydrograph, probably largely due to the cuvette not being well accounted for in the model. But after calibration, you get a calibration side, a validation side, and we do very well with the timing. I think our timing is very good. Yolanda's done an excellent job in getting the timing right. We have some biases in the absolute volumes. Some other gauges that are not daily but are historical, mean, monthly look pretty good too in terms of timing. With obviously you can see biases that are pluses and minuses across all these examples. So it looks quite nice, and the idea is, can we just pick a pixel on any river and say something about it? And so we have stream flow estimation for the lowest period, day of year, and the highest. And I think the highest is really interesting because it spills over into the south, and really this idea that the October-November peak rainy season and the bimodal dynamic is much greater, the rainfall coming in October and November. And so you have peak flows in the south in that time of year. Low flow is more symmetrical across the basin. Finally, to get to the question of the session, this is early work and not definitive, but taking land cover, having the model behave well, and then perturbing the land cover. So taking the rural complex and expanding it outwards from the trunk roads and having it replace all of the rainforest, for example, and seeing what that does to the hydrograph downstream at Kinshasa. And these are just some early results. And ET falls, rain generation falls under some assumptions of a climate feedback. And the early results, and I'm sorry, I'm not a hydrologist. If you ask me a question, I will not get the right answer. But the early results are showing that it's a loss of flow at Inga, which is the big hydro installation below Kinshasa. And the idea is to talk about ecosystem services. If, for example, the low flow period at Kinshasa and Inga in August drops 20%, that has big implications for power potential, and really you can turn the forest ecosystem service into dollar signs pretty clearly under some of these scenarios, I imagine. But that's just, and take a look at Yolanda's poster when we're out after the break. I think I'm good.
Are there any questions before the break, or before actually Landsat wants to say a word about the Landsat? So, are there any questions? Maybe one, two? No? Oh, yes.
First of all, really enjoying your fantastic presentation. And this is first of all, and it's very alarming to see how human impact could affect forest. And drawing from research over Amazon, so when the deforestation reaching certain threshold, and it is very likely you're going to change in rainfall regime, and that actually could further reduce the agricultural productivity. And so your work, to me, really draw attention to that kind of a scenario, perhaps worth to discuss or explore further.
Great, yeah, thank you.
Thank you. Venkat, you want to to say something, right? NSF and your support. Thank you.
While Venkat comes up to the microphone, I'll say thank you to NSF. Venkat is at NSF and facilitated a tremendous amount of support for the conference.
Thank you everybody for coming, and I'm sorry that I could not come on the first day. I was at another meeting. But my association with this Chapman is far earlier than NSF. I was the chair of the Chapman Conference Committee, which approved this original proposal, which was submitted in October of 2015. So,
Thank you.
So please don't get the impression that Doug wrote the proposal and approved it himself, though he's the chair. He could do that. He's pretty quick. But you know, on behalf of NSF, you know, we are always very happy to see these big science questions being asked and answered. As you very well know, many of people in this room may have already been part of it. Infuse closed yesterday, which was like, it's a huge program between GEO, SPE, engineering, USDA, NIFA. It's a big, big program. And some of the questions asked in Infuse, the innovations of food, energy, and water, is very relevant to the questions and hypotheses being asked here. You know, catchment and watershed boundaries are not constrained within the United States. You're going all over the place. Second thing is that I want to tell you a very interesting new program within NSF, which some of you probably are already a part of, which GEO has launched. We have a new assistant director, Bill Easterling, who is very interested in land use, land cover change, hydrology, etc. And he's launched a new program called COPI, Coastline and People. I'm sure some of you have seen these announcements. As a matter of fact, a COPI workshop is ongoing in Atlanta right now. It was yesterday, today, and tomorrow, if I'm not mistaken. And there's one in Chicago, too. I don't know if it's already over or it's going to be happening. So you can look at these lessons drawn from these kinds of conference to understand the interactions between coastlines and people. And so with that, I'm very thankful you guys all came, and it's a testament to Doug's superior marshalling skills to bring you all here. And it's raining outside, which is very good, because I always say, you know, when I see rain, I say job security. Because being a hydrologist, if it doesn't rain, you really don't have a job. So thank you very much for coming. And I know there are some people in the audience who may want to ask questions, NSF questions to me. And so I'm available at least till early afternoon, and I'll be happy to answer any questions. Thank you very much.
Thank you, Venkat.
Thank you. So I think that's the coffee break coming up. And the poster session, 11:30, we have to...
Well, I'll usher you back in. We have a little tighter schedule today, but go enjoy the posters.
You're going to get an email.